Hey everyone, and welcome. It is absolutely fantastic to have all of you focused learners joining us today for this explainer. I want you to just look around you for a second. Whether you're glancing at your smartphone, maybe adjusting a smart thermostat, or even just thinking about the anti-lock brakes in your car, the reality is the smart devices we rely on every single day, they are all powered by a hidden foundation, and that foundation is firmware. But how do we actually know it works? How do we ensure it's secure? Well, that is exactly what we're going to unpack today. Okay, let's dive into this. Here is our roadmap for today. We're going to cover software versus firmware testing, the real cost of failure, unpacking firmware validation, hardware in the loop, industry-specific testing, and finally, a bulletproof testing strategy. We're moving fast from basic definitions all the way to advanced methodologies like Hill and CI/CD pipelines because the stakes here are incredibly high. All right, kicking things off with Section 1, software versus firmware testing. And this brilliantly illustrates the core difference. When we talk about traditional software, we're talking about applications running on general-purpose hardware, like a desktop or a smartphone. It's a highly simulated environment, it's flexible, it's forgiving. If there's a bug, you just push a patch over the internet. But firmware is an entirely different beast. It is rigidly bound to embedded hardware, it operates right down close to the metal, and updates are incredibly infrequent. You literally can't just patch it on the fly with that same ease. So looking at this breakdown, you can see the complexity gap is just massive. Because firmware is so tightly coupled to the physical hardware, testing it requires way more than just a software environment. You actually need specialized hardware debuggers and simulators. Why? Well, because firmware updates are rare, and in many embedded systems, updating the firmware actually requires physical access to the device itself. You really have to get it right the first time, because an error isn't just a glitch, it's a complete system failure. Which brings us to Section 2. The real cost of failure. Now, what's really interesting about this slide is this staggering number, 78%. According to recent industry analysis, 78% of homes with smart devices experienced at least one firmware-related issue in 2024. Think about that for a second. We aren't talking about some niche problem. This is a systemic vulnerability sitting right in our living rooms. And the financial and security costs of these failures? They're astronomical. When firmware validation is inadequate, the fallout ranges from product recalls costing anywhere from $1 million to over $50 million, all the way to irreversible hardware bricking, where a bad update literally turns your extremely expensive device into a very ugly paperweight forever. But perhaps the most terrifying cost is security. Poor validation leaves persistent backdoors wide open. Take the recent vulnerabilities in Zyxel NAS devices, for example. Command injection flaws basically allowed a single compromised piece of hardware to become a beachhead for attackers to move laterally across an entire network. It's a nightmare scenario. So how do we stop these multi-million-dollar disasters? Let's get into Section 3, unpacking firmware validation. So the crucial point is understanding this semantic but absolutely vital distinction between verification and validation. Verification is all about checking the code against the design specs. It asks, are we building the product right? Validation, however, asks, are we building the right thing? Validation ensures the firmware actually meets real-world user needs and performs reliably in its true, chaotic physical environment, rather than just passing some sterile unit test in a lab. Because here's the thing, firmware rarely fails in isolation. Basic functional tests might prove that a feature works perfectly exactly one time under ideal conditions. But in reality, firmware fails at the boundary. It fails when hardware components interact, when there's intense timing pressure, when strict memory limits get maxed out, or during unpredictable power state transitions. Real validation absolutely has to stress the system under heavy interrupt loads and degraded communications because that's what happens in reality. To solve those physical boundary issues, we need the gold standard. Section 4, hardware in the loop. Now, the traditional approach of pure software simulation is great because it's cheap and easy to set up, but it has a massive blind spot. It completely misses the physical behaviors and the electrical characteristics of real hardware. A register in your simulation might behave flawlessly, but the actual silicon on the final board might have slight timing variations. Pure simulation simply cannot replicate the chaotic realities of physical hardware. Let's move to and see how this builds when we look at the real-world results.
pure simulation catches about 60 to 70% of bugs. Software in the loop gets you a bit higher. But when you integrate real physical hardware components with controlled environmental simulations, hardware in the loop, your bug detection rate spikes up to an incredible 90 to 95%. You are finally testing that critical hardware-software intersection exactly as it will exist out in the field. Let's ground this a bit and look at how different fields apply this. Section 5, Industry-Specific Testing.
Every industry has its own completely unique edge cases. Take the automotive sector. Embedded testing there isn't just about functionality, it is literally about life-saving compliance. They require intense safety traceability and fault injection, literally forcing the system to fail just to ensure it can recover safely. Over in IoT, or the Internet of Things, the big challenges are all about unstable cloud networks. Those devices have to handle sudden connectivity drops and interrupted over-the-air firmware updates without bricking themselves. Meanwhile, consumer electronics face incredibly short development timelines and must rigorously test battery behavior and power consumption across varying production batches.
So, how do we bring all of this together? Section 6, a bulletproof testing strategy. This right here is the exact structured 5-step setup process engineers use to replicate field conditions in the lab. First, you have to define the real-world operating scenarios. Second, you set up your hardware-in-the-loop hardware with the target interfaces. Third, you configure your simulation models for load and environmental conditions. Fourth, execute your automated test suites. And finally, analyze the results and iterate. Now, it's the automation in step 4 that is a total game changer here because it guarantees consistent, rigorous coverage every single time the firmware changes.
And let's be real, firmware changes constantly. That is exactly why implementing a CI/CD, or continuous integration and continuous deployment, regression strategy is absolutely essential. When firmware is getting updated daily, you just cannot rely on manual testing. You need a solid regression backbone consisting of automated build checks, static analysis, interface and driver tests, board-level smoke tests, and comprehensive test reporting. This automation is what protects your release baseline from nasty, late-stage integration surprises right before a product launches. We've seen the incredible engineering that goes into verifying that tricky boundary between hardware and software, and obviously the massive financial and security risks involved when that validation falls short. So I want to leave you with this provocative thought. The next time you turn on a smart device sitting in your own home right now, ask yourself, your devices are smart, but is their firmware truly secure? Thanks so much for joining me on this explainer. Keep asking questions, and I'll catch you on the next one.